Hello and welcome to Ztec's webinar on significantly improving the inspections of composite structures. My name is Wayne Waxman and I'm the Director of Marketing at Ztec. I'd like to thank everyone for joining us today. I have a couple of logistical items before we get started. Everyone in this webinar is on listen-only mode. We are recording today's session, so you will be able to review and listen to it or share it with colleagues in your organization. Everyone who is registered for this webinar will receive an email later this week with a link to the recording. During this webinar, there are some video segments. With GoToWebinar, when you play a video, the audio or sound for these segments only plays through computer speakers. So if you've dialed into this webinar through the phone, unfortunately, you're only going to be able to hear the video sounds through your computer speakers, not on the phone. Now, if you can't listen through computer speakers, don't worry about it. The videos are going to have subtitles, so you will see the text of what is being said. Finally, there will be a Q&A session at the end of this webinar where we will be answering questions. You don't need to wait until the end of the webinar to send in a question, though. If a question comes to mind at any time during this webinar, just type it in the questions box on your GoToWebinar panel. Before I turn this over to our presenter, Danielle, I'd like to give a quick overview of Ztec. Ztec is a global NDT leader. For nearly 50 years, we've advanced the science and standards in both ultrasonic and eddy current technologies. We've set new heights in inspection performance, productivity, and predictability. Ztec's proven expertise and complete product portfolio serve the inspection needs of our customers worldwide in transportation, power generation, manufacturing, and oil and gas. Ztec is a subsidiary of Roper Technologies. So let's get to today's presentation. I'd like to introduce Danielle Richard, Technology Manager, Phased Array Ultrasound at Ztec. Danielle has been with Ztec since 2014, and he's been working in advanced phased array UT product and solution development for more than 15 years. Danielle is Ztec's subject matter expert for the aerospace industry. With that, I'd now like to turn this webinar over to Danielle.
Thank you, Wayne. Hello, I'm Danielle Richard, Technology Manager from Ztec. And today, I will conduct a remote video demonstration of our time reversal technique for rapid and reliable phase array inspection of composite structure. This is the agenda for our demonstration. First, I will briefly introduce the inspection challenge, and then I will explain the principle of the time reversal technique. After that, we will look at the setup of this demonstration and perform live ultrasonic data acquisition on a typical composite specimen. We will then show the advanced analysis tool included in our UltraVision software, and finally, we will wrap with a summary and take your questions. So, what is the inspection challenge? Well, the aircraft industry uses an increasing quantity of composite material for the manufacturing of lighter, more fuel-efficient, and more comfortable airplane types. The composite component can have variable and complex geometries. For instance, the fuselage, the wing skin, stringer, and spars. The illustration on the right side of this slideshow a typical example of the composition of a modern commercial aircraft. Roughly 50% of the material used are composites. Due to the large manufacturing volume, there is a need for a reliable and high-speed inspection. Inspection after manufacturing of the composite structure must be able to detect various defect types introduced during the manufacturing process: porosities, foreign bodies, and delamination. The time reversal phase array UT technique is proposed to improve coverage and detection capability while maintaining a high inspection speed. So let's look at the concept of this technique. Time reversal is a real-time adaptative UT inspection technique meant to eliminate the effect of misalignment between the probe and the specimen. The technique uses a measurement and compensation of flight time of surface echoes of individual probe elements. This is why the technique is called time reversal. This is a two-step process, but both steps are performed real-time to maintain a scanning speed similar to standard phasary UT. The first step of the process is surface profiling. A plane wave is generated by firing all elements of the probe simultaneously. When the wave meets the specimen, it is reflected back. This reflected wave is no longer a plane wave because it was affected by the shape of the component. The variation in the wave shape then translates into different arrival time on each individual element as shown on the upper image. Using the different arrival time measured in the initial firing, the software calculates the delay for individual element that is necessary to compensate the difference introduced by the surface profile. This process can be repeated several times until the compensation is perfect and the incident wave is essentially normal to the surface, like on the lower image. The second step of the process is to record data using the surface adapted delay obtained during the profiling phase. Data acquisition is performed using electronic linear scanning with an appropriate active aperture, and the flaw is well resolved on the surface echo. As mentioned before, profiling and data recording are performed real-time in a single rapid scanning sequence. Our current portfolio includes several phasary instruments designed for the inspection of composite parts, using both regular phasary and time reversal phasary. Small, medium, and large-scale applications are supported respectively by the Topaz 32, Zircon, and Quartz instrument family. Topaz 32 is part of a family of integrated portable instruments. This line of product has 32 active element aperture over 128 total element support. Pulse voltage of 75 volt in phasary on a 50 ohms load make it one of the more powerful portable instruments available on the market. It has outstanding signal quality, supporting 16 bits digitalization up to a maximum range of 800% screen height. Its support of time reversal and homing gates, to name a few functions, make it a perfect match for field examination of composite components. The Zircon unit shares most of its electronics with the Topaz 32 and has similar performance capability with that one. But this unit is packaged in a different form factor, better suited for fixed location, controlled by an external computer. This unit also has a 32 active element aperture over 128 total element support. While the UltraVision Touch interface can be used to control that unit, the more complete UltraVision Classic is often preferred. And like the Topaz and Zircon seen before, the Quartz is also a 32-128 PR instrument. But this time, the focus is set on the integration capability of the instrument within an industrialized inspection system. For this reason, a rack mount form factor has been selected, along with an integrated probe splitter, allowing multiple probe support without using additional accessories. Having a data throughput of 30 megabytes per second and the capability of firing multiple apertures at once, inspection speed can be optimized by using this unit. UltraVision Classic is also the version of choice to control this instrument. And sometimes a single instrument is not enough to cover the inspection requirement in terms of coverage or speed. For this reason, our instrument can be used in an array configuration controlled by a single computer and acquisition software. Up to 10 instruments can be connected and used at once on a single system. In this situation, each individual instrument has complete probe support and access to its full data bandwidth. This is obviously designed for fully integrated or rack mount solution. While a single probe can be used in multiple paths to inspect a component, the efficiency of the inspection can be increased by using multi-probe at once, organized in a scanning head, ensuring a complete and total coverage of the component in a single inspection pass. Let's now look at the element of this first demonstration. We have a composite specimen with typical attenuation and a geometry that is characteristic for stringer and spars, component of airplane wings. It contains artificial brass insert along its flat area. The inspection will be conducted in a complete immersion, like it is mostly done at the composite manufacturer. Only the water tank is a lot larger than ours. A typical 1D linear phase array probe will be used to inspect the flat surface of the composite component. It is mounted on the linear mechanism for encoded scanning sequence. We can manually optimize or misalign the orientation of the probe to illustrate the capability of the time reversal technique to compensate for such misalignment. We will perform the data acquisition with a Zircon portable phase array unit with time reversal option. The unit is controlled by the ultravision software. So I will now launch the video.
For this first demonstration, I will be using this water tank. The composite component has already been installed within, and I will be using a flat linear phase array probe. This one is installed on a track and array system which is encoded. The inspection will be performed using a Zircon time reversal instrument that will be controlled by this laptop running UltraVision 3. So before starting the data acquisition, let me explain what exactly we are showing on the UltraVision screen. For the purpose of this demo, we have programmed two separate channels. The left part of the screen shows the various views for the standard phase array UT channel. The upper left part is the sectorial scan, and it represents a section of the component perpendicular to the surface. Next to it, we have the basic A-scan view, and below this view, we have a C-scan or top view of the component, showing the maximum signal amplitude at each position on the surface. This view is displaying the content detected within a gate set just after the interface echo and ending just before the normal backward signal. The time reversal channel is on the right part of the screen, and we show exactly the same set of view and signal as for the standard phase array UT channel. Before the start of this demo, we have optimized the alignment of the probe with the component in the water tank. And in TZDL condition, we don't expect to see any difference in quality between standard phase array data and time reversal data. Additionally, during preparation, we have performed an amplitude calibration and set both the interface and backward signal at 80% screen height. So let's perform a scan using this configuration. As expected, both the regular phase array channel and the time reversal channel demonstrate equivalent result in this situation. The reason being the probe is perfectly aligned with the surface of the component. Additionally, that scan is able to demonstrate that the inspection speed can be pretty fast. With the setup running two channels at once, I can run close to 100 mm per second scanning speed. Now, if I get back to one specific indication close to the back wall, we can have an overview of the effect of the time reversal feature. I will now induce a slight misalignment between the probe and the component. As we can see, just a slight misalignment of a few degrees will completely destroy the capability of regular phase array to focalize on the surface of the component. But the time reversal channel will be able to compensate for this alignment issue and maintain proper detection capability. In fact, with that techniques and this specific probe, I can compensate for, let's say, between 5 and 10 degrees of misalignment between the probe and the component. We can now perform a new scan with this probe with a slight misorientation issue. And we will be able to see that the time reversal channel will maintain detection and sizing capability, while at the same time, regular phase array will be long gone at that point. This illustrates properly the capability of the time reversal to compensate for alignment issue between the probe and the component and maintain detection capability in different scanning scenarios.
Now that the flat area of the component is scanned properly, we can continue the examination by looking on how to address the curved area of the component. In this demonstration, we will now use a Topaz 32 portable instrument instead of the zircon used in the previous one. The Topaz 32 is also using time reversal to optimize the result of this inspection. We'll keep looking at the same component as before, but this time we will focus on the curved area. That section of the component also has reflector embedded at different thickness. Material quality in this curved area show increased attenuation. One of the reflectors in this component has been improperly manufactured and has a weaker response during examination. This inspection will also be conducted in complete immersion, but this time using a manually driven probe and string encoder to illustrate the portability of this solution. A 1D curved phase array probe will be used to cover the OD, or convex area, of the curved section of the composite component. I will now launch the video.
To continue the examination of my component, I will now use a Topaz time reversal unit to perform the inspection. This instrument has been loaded with a setup equivalent to the one we've been using before, with a phase array channel on one side of the screen and a time reversal channel on the other side of the screen. This time, since I want to do the examination on the curved area of my component, I will be using a curved phase array probe installed on a support device. Since I want to do a manual scan this time, instead of using the rail system, I will be using a string encoder to record the probe location. I will now set up the probe over my component, and I will drag the probe across the corner area. And we now can see on the scan result that the time reversal channel has been able to detect and find every flaw that were present on that corner area, where for the phase array channel, we've been missing quite a few, for the simple reason that the probe is not properly aligned so that every element is able to cover the full corner area. I will redo the scan a second time. I will grab the probe, position the probe over the corner, and start moving the probe across. And I am expecting and obtaining equivalent result for the time reversal channel, where every flaw has been found properly, and still the phase array channel still are missing the bottom row of indication. This illustrates the repeatability of the time reversal function to correct for probe misalignment or probe orientation issue while doing manual scan.
For the two demonstrations that we have just performed, the ultrasound and time reversal parameters were already defined and tuned. In this next session, we will have a look at what it takes to set up a time reversal channel. We will look at the parameters that need to be defined and the various tools that can help us during the fine-tuning. We will also have a look at the actual impact on the inspection speed of using time reversal versus regular phase array. Spoiler alert, the effect on speed is negligible.
The process of using a time reversal channel is quite easy. The first step is to start with a channel that has every phase array parameter that you will want to use, as if it was a regular phase array channel. You will want to set all of your parameters to the given inspection need that you have. With this current setup, with two channel phase array without the time reversal feature activated, I currently have an acquisition rate of 48 Hz. For that second channel, I will go to the time reversal menu, and I will have access to the parameter needed to prepare the time reversal function. In that page, you will see the gain used during the profiling phase and parameter related to the profiling gate. Namely, you will see the start position of the gate, stop position of the gate, what is the threshold value for that gate, and what should be the detection mode for that profiling gate. With that setup, I'm currently asking for 4 iterations for the profiling. Once you have your parameter set up properly, you will toggle the time reversal to online, and you will see an immediate result on the top right corner of the screen. Just for comparison, I will go back to the UT settings, and I will note that the acquisition rate is now down to 45 Hz only. Original value was 48. So there is very little cost in actual inspection speed by using the time reversal function. The slight difference is due to the addition of the profiling focal loss, but other than that, all of the processing is done real time by the hardware, and the inspection speed can be very fast. Now back to the time reversal menu. There is also access to advanced parameter for the time reversal function. One of the very interesting possibility is to display the delay pane, which is a display of the current focal loss computed during the profiling phase. When we'll be moving the probe, you can see an actual dynamic update of the focal loss as they are recomputed. Another tool that is very interesting is the profiling tool. This one will reconfigure the screen display, and this time you will see two different things. On the left side of the screen, you will see a sector view and a scan view that are displaying the current result of the time reversal function using the current set of parameters. And on the right side of the view, you will see a sector view and an A-scan, but this time they are showing elementary data capture for each individual element as they are used during the profiling phase. This is very convenient to see what is the contribution from every element and what is the current probe orientation and where you should put your gate to catch properly the full interface echo. Now we can see as I'm moving the probe around that the interface echo can move quite a lot. Focal loss are recomputed on the fly to compensate for this alignment. And on the left side, the time reversal maintain proper alignment of the full signal. Once you are satisfied with your profiling parameters, you can accept the parameters, and you're now back to the original display layout, ready to do your examination using time reversal.
To allow the demonstration on Analysis tool, a scan of a flat reference standard has been performed before this session. In the plate, there is presence of three types of indications: a 1/4 by 1 inch, 0.7 by 0.7 inch, and 0.4 by 0.4 inch. The flaws are located at different depths, and due to the nature of their composition, have different amplitude response. Analysis will be performed using UltraVision 3 Classic interface. But before starting the analysis demonstration, let's review the goal and process for SNR evaluation. It is typical before and after an inspection campaign to validate if the inspection system, composed of instrument, probe, cables, and other elements, is sensible enough to detect the type of flaw we are looking for. To prove this sensibility, a reference standard is often scanned, and every known reflector in that reference standard is evaluated. If the SNR value is above a predetermined value for every measure indication, we can assume that the system is respecting performance criteria and can be used for the planned examination campaign. Now, the SNR computation itself is a multi-step process. True surface area of the reference reflector is known and named nominal area from this point on. During the analysis process, at least 75 of that nominal area must be detected. While this ratio of 75 is variable and subject to procedure, it is often used. We are naming target area this minimum surface area that must be detected. The user, helped by software tool, must evaluate the signal present within an indication. To do so, amplitude boundaries on amplitude C-scan or depth boundaries on position C-scan are adjusted so that the measure size of the indication falls just above the target research area. Knowing the boundaries used to find this area, we can perform the computation to obtain the SNR value. This SNR value takes into account a noise characteristic close to the indication and the boundaries value. High SNR value denote high detectability, while low SNR value denote poor detectability capability. So let's move on to the actual sizing demonstration itself.
For this demonstration, I will be performing the analysis of a flat reference standard. The goal of my session will be to determine the size and SNR factor for every indication present within that component. But before doing so, let's have a look at the tool I have at my disposition. At the left of the screen, I will see my palette tool, which is currently set to display the very common grayscale palette. One nice addition to that palette is the ability of displaying a special color for each extremities of the palette. For instance, if I'm going to the palette editor, I have the ability of activating a min-max color, which will apply orange or any custom color for the minimum value and green at the moment for the maximum color. I did a copy of my gray palette named min-max that will use this special color activated. So now, in my choice of palette, I can toggle at will between the gray regular palette or use the min-max color activated. In this situation, I will see that everything that was a saturation or at the extremity of my palette is now color green, such as this first indication over there. And everything that was at the other extremity of my palette is now orange. This is very convenient because if I'm rescaling or contracting the range of my palette, that will rescale the grayscale, and everything before and after that range will be color using this min-max color. It is very convenient to emphasize location of any indication present in my component. This tool can be tied directly with the SNR tool that I will show in a few moments. So let's expand this palette back to its original value, and let's toggle to the SNR tool to do the actual sizing. The SNR tool is the method by which we'll try to find what is the minimum area of an indication that is just above the nominal area of that same indication, and will determine what is the SNR factor of that indication in relation to a noise area. We will see on screen that I have the same significant value or readings on top of my screen. The first two are the characteristic of my noise, and then I have the current SNR factor and the currently measured area for the indication. There is three ways of using that tool. The first one being the most manual, then there is a semi-automated one, and the last method is a fully automated method that will be doing the SNR computation for us. So let's start with the first one. The first step in that process will be to define a noise area, currently set with the blue box. And within that blue box, I will have an average amplitude of 81.1% and a standard deviation of amplitude of 1.4%. This will serve as baseline from which we can compute the SNR value. Then I have to define which indication I want to work with. And for that, I will define another contour box enclosing the indication I want to work with. For reference, this indication is 6 mm wide by 25 mm long, or in imperial, a 1/4 inch by 1 inch. The nominal area of this indication is 161 square millimeter, and it is very common to try to dimension that indication at 75% of that nominal area. So for this one, I'm looking for a target area of anything above 120 millimeter. This is what the SNR tool on the left side will allow me. Currently, with the currently set SNR factor, I'm dimensioning that indication as 508 square millimeter, way too high. So I can now drag the SNR slider and try to aim for the first SNR value that will be just above the 120. I can either drag that on the slider, or I can also input the value directly in my field. And now close to 27 SNR value will be the value that is just above my 120 minimum reporting area. Meaning for this indication, I will have an SNR value of 27.2 that can be applied. Now if I want to reapply the same process for the second indication, I can drag my indication contour box and my noise contour box that will recompute a new characteristic for noise, and I can restart the process of finding the optimum SNR value. So currently that is close to 15. At any point in time, I can look what are the boundaries from the noise baseline that can be applied to dimension that indication. So from an average noise of 80.7%, if I'm applying a 15 SNR factor, This means that I'm looking for everything below 58% or everything above 100%. That is where I can link those boundaries with the palette tool to have a special coloring that will show me a contracted grayscale of what is the noise area and special coloring of everything that is measured as being the size of the indication. If, for instance, I do the dimensioning on the third floor or the third indication, I will set again, I will try to find the best SNR value. So currently a SNR value close to 30. And when I will link, I will see that all of the orange pixels are those that are taken into account to compute the current size of the indication. While being efficient, this is the most manual way of using the tool. A bit faster is to use the predefined area section, where I can predefine what are the size of the indication. For instance, I've preset my 25 by 6.3 millimeter for a 161 square size for a target research size of 120 square millimeter. The process or the early step of the process is still the same. I have to define what are the noise and indication area. But then instead of trying to find manually what are the SNR factor, I can simply press the auto threshold button and the software will compute for me what is the perfect SNR value for these input parameters. So the first one, we have a SNR value of 26. And then if I want to do the dimensioning of the second one, I can just click auto threshold again. This is very convenient when tied with the indication table, which will allow me to record all of these indications in a single table, in a single series of steps. So I will define the first one, compute the SNR value, add that to the indication table. Then I will dimension the second one, compute the SNR, add that to the table. And I can do so for every indication in quick succession. Currently I have 4 indications. Indication number 5 is coming. One of the advantages of this system is that we remove any user error. The system or the software is computing by itself what is a perfect SNR for the series of indications I'm looking at. Not only that, but we're also keeping track of not only the parameters, but the result for every finding. And we can also see for each indication, if we highlight any given indication, we can see what was the noise area that was used to compute each indication SNR value. We keep a complete traceability of the result. Once we are done with a series of sizing, it is very easy to generate a report or to export this result directly to Excel. And then within Excel, use that into any type of report that we have already defined. For some indication, like the one in the center over there, this one is 17.8 by 17.8 millimeter for a research area of 237 square millimeter. Now, if we try to find the threshold, the SNR value for this indication, we'll find a SNR factor that is kind of weak, 2.3 only. It may make sense for such an instance, instead of doing the sizing on the amplitude C-scan, to toggle and use a position C-scan. For some situation, it may be worthwhile because we can see on this specific scan that on the position C-scan, the flaw or the indication are very much more obvious. And the process is exactly the same. We define a noise area and a contour area for the indication, and we press the auto threshold button, and that will compute us a very high SNR factor. In fact, this is due to the noise area being a 0 standard deviation value. But even if there was an actual standard deviation different than 0, there's still a very big discriminance between the noise and this specific indication over there. So the tool works both on amplitude C-scan and position C-scan. Now, the third way of using the tool is, instead of looking indication by indication and try to size them, it is instead to try to find what is the rejectable value that I use. So let's say I'm defining this area as the noise definition, and I want to reject everything that is below 3.5 SNR. If I'm looking at my boundaries, this means I need to detect every indication below 74.5 and every indication above 85.7. To do so, we have a tool called Assisted Analysis that can do this research for us. It will scan the complete C-scan and will automatically position contour box over any indication that respect this criteria. So if I click on the process button right now, close, we can see that the software has automatically detect indication 1, 2, 3, 4, and so on, all of the indications that are outside of the current amplitude range that we've defined as a rejectable criteria for the SNR factor. All of these indications currently, the enclosing box respect the 3.5 SNR factor based on the noise definition that we are using. This works, again, both on the amplitude C-scan and on the position C-scan. This concludes the tool set that are used for sizing and determining SNR factor on composite component. Thank you.
So this concludes the planned content of this webinar. We have covered the concept of what is the time reversal technology and how it can be applied on surface with different and changing profile. We have seen the benefit of increased signal quality and repeatability of inspection results using the time reversal technology. We also saw that inspection speed is not impacted by using this advanced way of processing focal loss. We did a quick tour of sizing tool that can be used to evaluate indication size and determine SNR level. Furthermore, many of the evaluation tools we presented reduce the risk of operator mistakes during analysis and provide automated computation of indication characteristics. Last but not least, Ztec product line is already in use in several places in the world today, with manufacturing or services company relying on our system on a constant basis.
If you are interested in learning more about the time reversal technique or have additional questions, you can email us anytime, info@ztec.com. To learn more about Ztec, certainly visit our website at www.ztec.com, or you can certainly follow us on social media. We are on LinkedIn, Twitter, and of course YouTube. So this concludes our presentation today. I want to thank everyone for joining us, and hope you have a great day.